Hello folks, welcome back. In our last video we talked a great deal about the wave nature of the electron. Now one of the things we mentioned was the Schrödinger wave equation, which gave us probability in terms of electron location. And that led us to talk about something called an atomic orbital. And we're going to spend more time talking about the atomic orbitals today, so stick around. An atomic orbital is a three-dimensional region that we find around the nucleus. And these atomic orbitals are like fuzzy clouds of probability. In other words, the more dense the cloud is at a particular point, that means you'll have higher probability in finding an electron at that location. Let's take, for example, an electron at its lowest energy state, its ground state. If we were to compose a probability map, finding all the spots that the electron is located at particular instances in time, it would probably look something like this. Very densely populated toward the nucleus, but then as you get further away from the nucleus, more fuzzy, less dense. So the high density of dots near the nucleus tell us that we're more likely to find an electron in that location. Now this isn't 100% because there's no definite boundary on these clouds, so it's also possible the electron could be further away from the nucleus. We're saying this is the most probable location. That atomic orbital has a fuzzy boundary, so we can't say it has an exact defined size. Instead, the orbital is drawn to account for about 90% of that electron's total probability distribution. So in other words, 90% of the time, the electron is going to be found in that orbital as it's drawn. Remember before about how we assigned quantum numbers to these electron orbits. We called it n. N is the principal quantum number. As the value of n gets larger, that means that the electron is going to be further away from the nucleus. Therefore, each value of n specifies a major energy level within that atom. So we can call n a principal quantum number or a principal energy level. The lowest energy level of an atom is going to have an n value of 1. We call that the ground state. In the research concerning hydrogen, 7 energy levels at this point have been detected, and so that n value could be anything from 1 to 7. Depending on how energized that atom is, you could find the electron at n equals 1 all the way up to n equals 7. So again, n represents our main energy levels. But within those energy levels, we have what are known as sublevels. If you have a building, you could think of the main energy levels as floors of that building. But then, within those floors, you might have suites, where you have a grouping of rooms put together. That's sort of like the sublevel. What we find in the atom is that in principal energy level 1, or n equals 1, there's only one sublevel, one suite. As we increase our value of n, we also increase the amount of sublevels we have. So, principal energy level 2 has 2 sublevels, principal energy level 3 has 3 sublevels, principal energy level 4 has 4 sublevels, and so on. This is sort of like what we see in theater seating, right? Sort of wedge-shaped where you have fewer seats toward the front, but as you move away from the stage, you get more sections and more rows. So the number of sublevels increases as the principal energy level increases. You might recall we said before that these orbitals were brought about by mathematical means. So it's interesting to note that the orbitals have different shapes. That is, different probabilities of electron locations from orbital to orbital. These orbitals have been given letter designations to differentiate between each type of shape. The s orbitals are spherical shaped. Each principal energy level will have an s orbital. P orbitals tend to be more dumbbell shaped, as you can see. Here are the shapes of the d orbitals, and then here are the shapes of the f orbitals. It's important to understand that only 2 electrons can fit in each one of these orbitals. So for energy level 1, or n equals 1, I only have one sublevel. That's the s sublevel. I'll call that particular sublevel the 1s sublevel because it's the s sublevel on the principal energy level 1, 1s. Going to the next level, n equal 2, I have 2 sublevels, an s sublevel and a p sublevel. Now remember, the s sublevel only has one type of orbital, but the p sublevel has 3 types of orbitals. Going back to our building analogy, we would say that the S suite is just one room in that suite. But the P suite of rooms would have 3 rooms. So on my second principal energy level, or n equals 2, I have a total of 4 orbitals on that level. My S sublevel has 1, and my P sublevel has 3. And remember that 2 electrons can fit in each of those orbitals. So on the third principal energy level, or n equals 3, I now have 3 types of sublevels. I have an S sublevel, I have a P sublevel, and a D sublevel. Remember that the S sublevel only has 1 orbital, or in our S suite, we only have 1 room. Remember that the P sublevel has 3 orbitals, or going back to our building analogy, the P suite has 3 rooms. The D sublevel has 5 orbitals, or the D suite has 5 rooms. Therefore, in that third principal energy level, in other words, n equals 3, we have a total of 9 orbitals on that energy level. And again, recall that each orbital can contain up to 2 electrons. When we get to principal energy level 4, or n equals 4, now we have 4 types of sublevels. We have the S sublevel with 1 orbital inside. We have the P sublevel with 3 orbitals. We have the D sublevel with 5 orbitals. And we have now the F sublevel with 7 orbitals. In naming specific sublevels, I would use the principal energy level followed by the sublevel in question. In the second energy level, n equals 2, I have the 2s sublevel and the 2p sublevel. You get it? The third energy level, I have the 3s sublevel, the 3p sublevel, and the 3d sublevel. You could think third floor S suite, third floor P suite, third floor D suite. By the way, if you are trying to figure out how many total orbitals you have on a particular energy level, you can do it very quickly by simply squaring the value of n. When n equals 1, you only have 1 total orbital, the 1s orbital. When n equals 2, you have a total of 4 energy levels. You have the orbital in the 2s sublevel, and you have the 3 orbitals in the 2p sublevel. On the third energy level, n equals 3, you have a total of 3 squared, or 9. We have the 1 orbital in the 3s sublevel, we have the 3 orbitals in the 3p sublevel, and we have the 5 orbitals in the 3d sublevel. That makes 9. So how many would we have on the fourth energy level? Right, 16. We have the single orbital in the 4s sublevel, we have the 3 orbitals in the 4p sublevel, we have the 5 orbitals in the 4d sublevel, and I've run out of fingers. But we have another 7 orbitals in the 4f sublevel. So 9 and 7 make 16. So in that hydrogen atom with its 1 electron, that electron can only occupy 1 orbital at a time. All the other orbitals are empty. In our building analogy, they are open, they're vacant. But when that atom gains energy, the electron becomes excited and moves to a higher orbital. Depending on how much energy it receives, that electron can move to the 2s orbital, or to a 2p orbital, or to any other orbital that's vacant. That's all we'll do for today. In this video, we talked about orbitals, how they are fuzzy clouds of probability, but they tell us approximate locations of the electrons in the space around the nucleus. We reviewed the idea of n, or the principal quantum level or principal energy level within an atom, and then we talked about sublevels within those energy levels. We also talked about orbitals and the different shapes of the orbitals and how those orbitals are arranged within each sublevel and within each quantum level. Next time, we'll talk a little bit more about how those electrons fill those orbitals we talked about today. We'll discuss the idea of electron configuration in an atom of a particular element. I hope this has been helpful to you. Until next time, God bless.